All settled down, got your breakfast, all that kind of important stuff in the lecture theatre. Before I go on to start, last week we did 3 lectures on electric properties of materials. This week we're going to do 2 lectures. I emailed you that although it's written down as a problem class for Friday, especially with the exam being on Monday of week 5, I'd like to get in to finishing the whole of, if you like, the original parts of the course as soon as possible. So we'll go straight on to lecture 32 on magnetic materials on Friday, and then back here next Wednesday I'll finish the course with ferromagnetism. So just before we start on the actual magnetic properties, it was just to mention that we had a very simplified view of electrical properties of materials. In particular, we only really considered them in a uniform electric field. So we imagine that we had a capacitor and we put a slab of dielectric in it, and we saw that in a homogeneous material, in a homogeneous field, remember all the field lines are just pointing through the capacitor, and the field strength is everywhere constant due to the parallel plate capacitor geometry, and we saw that we got some surface polarization charges on the material. Well, of course, I think it's obvious by symmetry that the attraction of the dielectric slab to this plate is equal and opposite to the attraction of the dielectric slab to the other plate. So we got no net force on the dielectric material. But that's only the case in a uniform field. So just to emphasize that we did brush some problems under the carpet. If we've got a non-uniform field, let's say for example up here in this corner, this positive, we've got a Van de Graaff generator or something that we've just produced an electric field where the lines are spreading out, in that case with roughly spherical symmetry, then in the dielectric object, of course, we still will get this effect of polarization charges produced on this side of the material being negative and on this side of the material being positive. But in this case, we don't get the neat cancellation that we got in a parallel plate capacitor, because the negative charges on this side of the object are in a region of higher field strength. These electric field lines are spreading out. So the force on this side is not balanced by the force on this side, because these charges are in a lower electric field. So the net effect, if you have a dielectric object, even a linear isotropic homogeneous dielectric, which will still give these surface charges, it's necessarily attracted into the region of high field strength. So basically, dielectric materials are always attracted towards regions of higher electric field strength, and it's only in the special case of the parallel plate capacitor that there's no net force on the dielectric object. So again, it's often the way that the very first things we study in electricity and magnetism are very complicated. And I don't know whether you did it at school, but you charge up, it can even be a comb that you charge by friction. It will pick up pieces of paper. And the reason is that the field lines are spreading out, whether it's from a Van de Graaff generator or your comb that's been charged up by friction. The field lines are spreading out. So the bits of paper are uncharged, but because they get polarized by the field and the different sides of the piece of paper are in different field strength regions, it gets attracted into the field. So you can pick up pieces of paper with a charged cone. Now, so although I'm getting slightly ahead, we're going on more to magnetic materials on Friday to emphasize from the outset, and we can't get away from it, magnetism is the magnetic properties of materials are more complicated because, and again it's important in this diagram, Fig 125, as I say, we'll come back to this on Friday, that the field is inhomogeneous. You see this magnet is sketched here with a strongly pointed pole for the south pole and a flat pole for the north pole. So the field lines, although we wouldn't be able to calculate them exactly with the techniques we've used, you can imagine, of course, that this is an inhomogeneous field. The field lines tend to bunch around the sharp pole. Well, by no means the case now that all objects are attracted into an inhomogeneous magnetic field. And the example given, a small cylinder of bismuth is weakly repelled, and that is like and this will happen in any system where you've got all the electrons are paired up. Whereas if you put a piece of aluminium into the same inhomogeneous field, it's attracted towards the sharp pole. So already we've got a difference in behaviour. All dielectric objects will be attracted into an electric field, inhomogeneous field, but in magnetism the bismuth is called a diamagnetic material. It's actually repelled by the sharp pole, whereas a piece of aluminium, this is an example of a paramagnetic material, is attracted. So right from the outset we have to be conscious of the idea that the magnetic materials are a little bit more complicated. And in particular, iron, cobalt and nickel will lead to a special treatment in lecture 33, the so-called ferromagnetic materials. So, just like we tried to understand the properties of electric materials in terms of electric dipoles, we're going to attempt to understand the properties of magnetic materials in terms of magnetic dipoles. Now, again, what is a magnetic dipole? So first of all, a magnetic dipole doesn't have to be rectangular, although that's easier from the calculation point of view. It could be a circle, but it's any current loop. So you see we've got a current just flowing around a small closed loop of material. And again, in the case of the rectangle, let's let the dimensions of one side be B and the dimensions of the other side be A, and then we seek to calculate the field at some distant point P, where this distance R from where we're calculating to the centre of the magnetic dipole is much larger than the dimensions of the dipole. So the way that calculation is done, and again with this lecture theatre and with the limitations of going through calculations, I'm going to refer you to the VLE notes for the details of the calculation, is that it's done by using the vector potential. Now I've already mentioned that we're not going to have that on the exam syllabus, so I'm not going to go through the details of the calculation, though I hope very much if you're particularly a theoretical physics or maths and physics student, you might have a look at it on the VLE. The idea is straightforward, and that is, first of all, we basically consider the current loop. First of all, let's take these two sides of the loop, and I hope you remember, it's way back when, it's in fact serves as a piece of revision, I brought these notes along, that you make an analogy. This is not, of course, the loop is not really charged at all, yeah? But it's a mathematical analogy between electrostatics and magnetostatics, that the equations for the x, y and z components of the vector potential obey the same equation as Poisson's equation. So what you do, again this is just the idea of the calculation, is that you replace the real system by a system, an analogous system, in which you have a lot of negative charges on one side and a lot of positive charges on the other. It's then relatively straightforward to solve Poisson's equation for this system, and then having solved Poisson's equation for this system, you map it on to the vector potential, just like given a charge distribution you get the electric potential, given the x, y and z distributions. And here, if you've chosen your axes intelligently, you've only got one non-zero component of the current density. So as drawn there, you just have to solve this equation. That gives you the x component of the vector potential, and then you calculate the magnetic field from taking the curl. Of course, this final step in the two calculations is completely different. Now, you might make the analogy between this equation and this equation to get this x component of the vector potential, But then your final step in calculating the magnetic field is completely different because you have to take the curl of the vector potential to get the actual magnetic field. So that's the idea of the calculation, and it's very similar to what we did in lecture 5, where we had some, in that case the current density was just flowing along the z-axis, and so the only non-zero component of the vector potential was in this case the z component, and then we calculated the magnetic field at some point P, and we were able to show that it circulates around the wire and obeys the same equation that we got from Ampere's law. So it's a slightly more detailed version, but it's effectively the same calculation. Instead of having one wire and calculating the vector potential, then the magnetic field, we've got 4 wires, which we consider in 2 pairs. So, as I say, I'm not going to go through the details for that. So it is possible, and this was discussed in lecture 5, to use the vector potential A to calculate, and in lecture 5 all we did was calculate for a single straight wire to calculate the magnetic field of a current carrying wire via, again, emphasising that with the vector potential, although we make this analogy between Poisson's equation and the equations of magnetostatics, we then have to take the curl of the vector potential to get the physically real magnetic field, and that calculation was illustrated there in figure 26 of the course handout. So similarly, of course the calculation's a little bit more involved when you've got effectively 4 little wires to consider in the loop, but just like in this case, what we did was that we replaced the real problem of the current carrying wire with the analogous problem of simply having a charged, single charged wire. It's not really charged, but this is the analogy with Poisson's equation. And again, it was first year electrostatics to calculate the electric field of a infinitely long charged wire, map the solution onto this one. So that was the analogy. If we now take that to this physical system here, we can do the same thing. So similarly, we can calculate A and B for a rectangular loop of wire. And this calculation, if you like, is just illustrated in figures 121 and 122 of the course handout. So that's the. I know, some people do, of course, find it unsatisfactory if I leave out some derivations, but I'd like to get into the properties of the magnetic materials as soon as possible. So the calculation is given on the VLE notes of pages 31.1 to 31.4. As I say, it's a longer calculation because, of course, we've got to sum up the contributions of the different wires. So the answer, cutting right through the whole of the calculation, at least I've tried to explain the philosophy of it. The answer for the Z component, it's already written up on the view graph there, is BZ is equal to mu naught. I'll define this mu in a minute. This, of course, is just the permeability of free space over 4 pi into 3 cos squared theta minus 1 over r cubed. This is the actual, and again you can of course calculate the z, x and the y components of the field as well, but I'm just going to concentrate on the z component, so I'll make that equation, 31, 2, where mu is equal to IA with A, the area of the loop. So this is the answer. The calculation, as I say, is a little bit more involved than the one we did in lecture 5. And because I say I've taken the vector potential off the exam syllabus, that's a little bit more advanced, although it's nice to see how it works. So we've just skipped to the answer. So that's the magnetic field of a small loop. And I should emphasize, first of all, let's do the definition. The product, mu, product of the current flowing through the loop and its area, the product mu is called the magnetic dipole moment. That's its full description. You'll often in books just see abbreviated to magnetic moment. Strictly speaking, it's a magnetic dipole moment of the loop. So, comparing equations 31-2 and back to last week, it was, and I've kept it as on the VLE notes, 2810, which was the expression for the electric dipole. We see that BZ behaves like EZ for an electric dipole oriented along the z-axis. So the physical systems are very different. Our EZ, I've written it down here at the bottom just for convenience, it should be in your notes. I went through very, very explicitly the calculation of the dipole potential for two charges oriented along the z-axis. So we did this calculation in some detail last week, where we oriented a coordinate system where this was the z-axis, and we put a plus and a minus charge symmetrically about the origin, some small distance d apart. And what we found was a field which had precisely this dependence both on the angle, and again here the angle is defined in a very similar way, that this angle here will be the angle made with the z-axis where the loop is oriented in the xy plane. And all that we've got to do is, of course, we replace the fundamental constant of electricity with the one of magnetism. The dipole moment is now interpreted as the current times the area of the loop in the xy plane, whereas previously this was the charge plus q and minus q separated by the distance d. And you can see we've got an exact analogy, and that's precisely why a little current loop is called a magnetic dipole, because it gives an analogous field to the electric field of a dipole of two plus and minus charges. Now you might think that that is extremely weird, because you've got completely different equations for electrostatics and magnetostatics. So if you've got these analogies, just fish that out here, go right back if you like to lecture 1. Remember, again, we're in this very simple case that the electric dipole we derived in the electrostatic case. This is a magnetostatic case. We've just got a steady current flowing around the loop. We're not taking into account any of the Faraday's law effect or Ampere-Maxwell law effects. We're just in these straightforward static approximations. And you might think, well, this is extremely unlikely that the solution to the field equations for a field with zero curl and finite divergence somehow come out to be the same as the field equations for a zero divergence field with a finite curl. And you think, well, you know, that simply can't be possible. The reason that it works is that we're extrapolating into a even simpler kind of approximation, because we've got these two sets of equations, but remember the key here is that the electric dipole expansion was only true if we had R much greater than D. So when we did the electric dipole, we took the approximation R is a lot greater than D, where the charges were separated by D. In this calculation here, we take a little current loop, where it's a rectangle with sides B and A, but the distance at which we're calculating the field is much greater than the dimensions of the loop. So in other words, we're looking at the fields in the regime because of this distance where we're far away from the sources. When we are looking at dipole approximations, we're actually extrapolating into the region where we're so far away from the charges that this is tending to zero for the divergence. But likewise in magnetostatics, we're so far away from these little current densities that we are tending to a zero curl. So if you like, we're now solving the cases del dot E is naught, del cross E is naught in the electric dipole approximation, and del dot B is naught and del cross B is naught in the magnetic dipole approximation. So as we get far away from the source of the field, and the source of the field in this case was the slight separation of the charges, so we're slightly closer to one than the other, and we have this similar approximation here. So it's a funny situation that these apparently very different types of, if you like, field equations give rise in both cases, because everything's tending to zero, to the same approximation, which is called the dipole approximation. Now, I haven't derived the approximation for you. I would just like to mention, it was more or less in passing, you can also get the approximation, this very complicated looking figure here. There's a completely alternative route to the vector potential, which is to analyse the forces on a current carrying loop. And there was your old friend Bill, as some people call it, B-I-L, where L is the length of a current carrying wire. That's its length. It's carrying some current I, and it's in some magnetic field B. You get this force on it. This is, of course, all in terms of magnitudes of vectors here. And this would be a current, if you like, vector. And if you analyse the forces on a current carrying loop, you can get to exactly the same formula. So there's a different way of doing the calculation, which I'll just mention in passing. So just make a note on that. The maybe surprising result that the E fields and B fields, let's just move that out of the way, have the same functional dependence arises from the, to continue this on the other board. So we've got, as I say, and I didn't do the calculation in detail, you do get this equation. It exactly resembles the field that we calculated in lecture 28 for the electric dipole, and this arises because of the approximations R is much greater than A and B in the magnetic case for the magnetic dipole, and R is much greater than D for the electric dipole. And the result can also be obtained. Again, I thought, well, it's an alternative, but I'm not going to go through that one either, because you can imagine that basically it's the kind of thing you've done in Newtonian or Lagrangian mechanics, that once you've got a well-defined force and you've got well-defined masses for this little object, of course you can analyse the forces can be obtained from analysing the forces on a current carrying loop. Yeah? Arises from the, thank you, not very grammatical, it's a bit tricky following, arises from the approximations. The force, yes, thank you. Wasn't the most grammatical sentence I've ever written, that one. And that's illustrated in figure 124 of the course handout. So we get this, this approximation, and one of the things, although I've not done, if you like, the derivation, again, I just mentioned this in passing. This force law itself, of course, we've done this several times. It just follows from the Lorentz force. If you analyse all of the charge carriers moving with some velocity v inside a wire, and each one of them, of course, experiences the force F is Q v cross B, and then you turn this, using the kind of arguments we've used many times, into a picture of current density, and then we integrate over the area of the wire, we get F is BIL. And being as we know that for all of the four sides of the loop, we can then go on to analyse the torque on the loop. Incidentally, just like with the case with the electric dipole, you remember that we had P equals QD was a scalar equation, and here I've written mu, the magnetic dipole moment, is equal to IA as a scalar equation. Often you'll see written that the magnetic dipole moment, which is perpendicular to the loop, this is perpendicular to the loop, is often written in this way with a vector current, but we've not really used that a great deal, just like you can make this one a vector equation where this points along the z-axis. If we choose the loop to be in the xy plane, then this points along the z-axis. This is the magnetic dipole moment of the loop. So those are the, if you like, the basics, and I've written here a complete analogy. Don't worry, this is all in the VLE now. Don't try and sort of like scribble this all down at one go. So the physical systems are completely different, yeah? We've either got a current going round in the xy plane or two charges separated along the z-axis. But because of the nature of this, the approximation, where we're a long way away from the sources, we get the same results for the field. I haven't done much on the x and y components of either field, but you can prove that they have the same functional dependence as well. The analogy between the electric dipole moment and the magnetic dipole moment is straightforward. Again, this result, the torque in an external field, that's derived in Young and Friedman, you know, the first year book. That's basic mechanics, given that you've got a little vector dipole moment in an electric field. The torque is a cross product of the two. Likewise, and again that's used in that calculation in figure 124, the torque in a B field is an exactly analogous equation. Again, I referred you back to Young and Friedman for this formula, and again that's explaining that you get a lower energy if your electric dipole is oriented in a certain way in an E field. Likewise, you get a similar equation for the B field, the energy in a B field. So a magnetic dipole tends to turn in a B field just like an electric dipole tends to turn in an E field. But again, this magnetism is more difficult. You'll notice this has got a subscript. This is the mechanical energy, because energy is also required to maintain the current in the loop when you move it in a B field. So there's a slight subtlety there in the magnetic case. Dielectrics are always attracted into a non-uniform E field, whereas ordinary matter can be attracted or repelled by a non-uniform B field. So there's a lot of analogies between magnetic dipoles and electric dipoles, but you also have to be careful that there are some differences as well. So what I'd like to do at the end, at least because I've sort of glossed over the details of the calculation, is at least to show you that our formula is completely consistent with what we derive by the Biot-Savart law for the field on the axis of a current carrying loop. So hopefully the view graph is in here. Again, this serves in a sense for a bit of advanced revision as well, that in a previous, I think it was in lecture 6 on the Biot-Savart law, we calculated the field on the axis. Now precisely the power of the vector potential is that what we've done with, remember now, if this distance x becomes very large compared with the radius of the loop, we should get the dipole approximation field at this point. The strength of what we've done in our formula, which of course being in VO45 has now disappeared from the board, if you've got, let's go back to it just here, so this field, remember, is calculated from the vector potential anywhere. So in other words, we could easily take this point P here off the axis and calculate using this field. And exactly that's where the vector potential is much stronger, because if you calculate at a point P like this with the Biot-Savart law, and you've got this cross product under the integral sign, it's a brute of a calculation to perform. Whereas as you see, if you look at the VLE notes, it's relatively simple to derive this via the vector potential. But let's check that we get the same results both ways. And you know, because clearly this formula that we've derived here, the one, let me just sort of underline it with my view graph pen there, that formula must hold on the axis. So let's check that we get the same result as we did with the Biot-Savart law. So again, of course, you all instantly remember the formula we did get, which is, don't all shout at once. I don't want to get deafened up here. Anyone remember what we got? I bet nobody does. So I'll write it up for you. So using the Biot-Savart law, and this was studied in lecture 6, we found, and this was, again, there was a question on this in the coursework, a squared over r cubed, let's make that equation 31(4). Sorry, again, there's a missing equation. I'm making the equations agree with the ones on the VLE notes because of having just skipped over a not very important equation. And this was for a circular loop of radius A. And that calculation was illustrated on, it's up there at the moment, figure 27 of the course handout. So on the axis, theta is 0. Remember, we're now comparing with a calculation where we've got a current going round a loop here, and the magnetic dipole moment, remember, is perpendicular to the loop, and we have got the angle between the magnetic dipole moment, which is perpendicular to the loop, and the vector connecting the centre of the dipole to the point where we're calculating. Well, obviously the angle between those two vectors is equal to 0, so cos theta is equal to 1 when this point P is on the axis here. So immediately on the axis, theta is equal to 0, cos theta is equal to 1. So equation 31(2), this is our new equation for the magnetic dipole here, becomes Bz is equal to, well, we've got the mu naught mu over 2 pi, excuse me, over 4 pi, I'm getting ahead of myself in the calculation. 3 cos squared theta is just 3, so minus 1 is 2, times 2 over r cubed. So if we take this new formula for the magnetic dipole and we plug in that we're actually on the axis, all that we do is we've got to replace this by a 2. And I've mentioned before that this is, even back in lecture 6, that we got an inverse cube magnetic field, and of course we have an inverse cube dependence. Now, using the fact that this mu is IA, yeah, that's our definition of the magnetic dipole moment, is the current times the area, but it was a circular loop that we calculated for, so it's mu times pi a squared. And again, because I'm short of board space, I'll just do the cancellation, maybe just in the crossing out a different colour here. So clearly I've got mu I can replace by I times pi a squared. Obviously now this pi cancels with this pi. The 2 here cancels with the 4. And you see precisely I've got mu naught I a squared over 2 r cubed. Yeah. So, yes. Oh, thank you. Mu is not equal to mu times pi a squared. It's equal to I times pi a squared. Thanks. So you can see that, again, I mean, this is just a very obvious summary of where we've got to, that the sorry, it's made that a bit confusing having that all up at the same time. So the calculations agree on the z-axis. So I've not derived this formula from first principles, but at least I've shown that it gives you the right sort of field. I'm now just going to, again, without a great deal of proof, because like to crack on, as I say, we're going to use these results in an attempt to understand magnetic materials next week. So we can also prove, and this one again is now see pages 31(7) and 31/8 of the VLE notes. So again, these proofs are given, but they're not so important really to us as the results in this case, that the torque on the loop is given by torr. I know different people use different letters. I'm following the Feynman lectures, so I'm going to write torque as a Greek torr, in this case mu cross B, and in the VLE notes that then comes out as equation 31/7, and I've mentioned this where mu has magnitude. Mu is equal to IA, and direction perpendicular to the loop. So this is slightly unsatisfactory that I'm going straight to the results. Again, this one and this one are discussed on the in more detail on the VLE notes. So there's this very beautiful analogy, and this, of course, this is, as I say, precisely why we call a small loop a dipole. I don't think it's obvious when you look at it that a current flowing round a little loop is going to behave incredibly analogously with two charges separated along the axis, but it does. And I'll make this comparison. So equation 31/7 corresponds to the relation that torr is equal to P cross E for an electric dipole. So the analogy is very, very complete. An electric dipole in a uniform electric field. And this again, the page number may have changed in the latest edition. In my copy of Young and Friedman, that's on pages 735 to 736. Again, that's more kind of first year mechanics, and not going to just keep revisiting straightforward calculations like that because we've got quite a lot to cover. Sorry, I just lost my microphone for a minute there. I'll try and re-stitch it back together with my collar. There we go. Similarly, we have that U mech equals minus mu dot B. So this one becomes, on the VLE, you'll see how much I've missed out. This one became equation 31/25, corresponds to U is equal to minus P dot E, 31/26. And just to prepare us for, as I say, you kind of think, well, so magnetism is going to be just like electricity. We're going to have all these little magnetic dipoles lining up in an external magnetic field, and everything is just going to run exactly like it did for our discussion of dielectrics. If only it were true. But, well, no, of course, magnetism, in particular ferromagnetism, is used as the basis for all storage of information. So, we want to understand it even on a qualitative level. But one of the things that is going to be a feature of our study of magnetic materials is that in the end we are not, emphatically not, going to be able to account for electron spin. And once we get inside magnetic materials, we really have to use quantum mechanics. So this is a classical field theory that I've been presenting last term and this term. And of course, although it's perfect in free space and it works inside, the Maxwell equations are still true inside materials, but inside materials where you have spinning electrons, we're sometimes going to find a complete breakdown of the analogy. And so when we look at ferromagnetism in particular next Wednesday, we're going to basically move completely away from stuff that we can understand just in terms of little currents going round in circles. Real magnetism is a lot more complicated than that. And so just to flag up already the problem here, there's a problem here that this has got a subscript, this hasn't. There's already a problem there. That note that UMech is not the total energy of the current loop. So there's already a subtlety here that didn't exist in electrical materials. And again, I'll just mention this in passing because the energy required to maintain the current has not been taken into account. Close brackets. I've made a few grammatical blunders, but I thought I'd close that bracket there for the sake of completion. So our kind of philosophy next time, as I say, I'm bringing that lecture forward to Friday so that we can put all the revision and problem classes together to the end of term. If you like, the approach is going to be almost like the Bohr model of the atom. Yeah? So what I'm going to do is pretend as if I can treat an atom as an electron going round in a circle. Now you already know that that's an incredibly naive model compared with the Schrödinger equation. However, one of the things that will come out of it, the reason that I'm going to pursue the classical analogy is that the classical analogy will say, oh, I'm going to have some mu, which is a magnetic moment which is in the plane perpendicular to this. And just as in classical, I'm going to derive the classical result that this mu is proportional to the angular momentum of the electron going round. And this is true. So the classical part that's going to work for us is that if I use a kind of Bohr model of the atom, I know you've gone way beyond that in sophistication, but applying the quantum mechanics of atoms and molecules in an external magnetic field is quite difficult. So it's good at least to start with an analogy where an electron just whizzes round a circle and produces a magnetic moment. And we'll find that actually for orbital angular momentum, we also get the right constant as well. So it's worth doing, but at that point, the classical analogy, it goes this far. It's okay here, and for orbital J, we even get the right constant here. So we'll come to this next week. This is just to give, on Friday, give you the idea. And so for orbital angular momentum, this very crude classical picture gives us a reasonable idea of what's going on. We get a mu that is proportional to orbital angular momentum, and we get the right constant from a classical model. But, of course, as you know, angular momentum comes in integral multiples of h bar, and that is completely beyond anything that we can handle in this course. And indeed, if you pursue any classical model too far into magnetism, you basically get the wrong answer. And in particular, this last point here, it's like, again, just to give, it is a complex field, so to give you this overview, is that the behaviour of paramagnetic materials, the ones that are attracted into a magnetic field, is just similar, not exactly the same, but similar to what we've done for electric dipoles. So in other words, you can imagine that if we've got a system which is attracted, just like the dielectrics are attracted in the paramagnetic materials, the equations are almost identical between paramagnetism and the dielectric constant. But we'll get no understanding whatsoever of the diamagnets, the ones that are repelled. And indeed, we'll end up with the kind of, if we follow it through, with the sort of absurdity of having a negative magnetic susceptibility. Anyway, we'll come to this puzzling field again on Friday.